Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, welcome to Lesson 11, Solution Sets for Equations and Inequalities. So we're talking about solution sets. Okay. Example 1 says to consider the equation x squared equals 3x plus 4, where x represents a real number. Now remember from the last lesson or a prior lesson, a number sentence is a sentence that has an equation, an equal sign in it, and it has just numbers. It does, and like pi is considered a number as well, but it does not have variables like x, unknown values. So this is not a number sentence, but it is an algebraic expression or equation. But part A says, are the expressions x squared and 3x plus 4 algebraically equivalent? Well, no, we have an x to a power of 2, and then that is a quadratic function, and we have a 3x plus 4, which is linear, so they are not algebraically equivalent. So we'll just say no for now. Part B says the following table shows how we might sift through various values to assign to the variable symbol x in the hunt for values that would make the equation true. So if we have that equation, let me keep that up here. So it's x squared equals 3x plus 4. So we're using this equation right here. Let me highlight that. So we're using this. Okay. So now it says let x equal 0. Well, if I plug 0 into that, I'd get 0 equals 0 plus 4, which is 4. That is false. And we're just picking random values here. Let x equal 5. Well, 5 squared equals 15 plus 4. No, 25 does not equal 19. 36 does not equal 22. 49 equal to negative 21 plus 4, which is negative 17. No. 16 equals 12 plus 4. 16, that is true. Okay, so x equals 4 is a solution to this equation. Let x equal 9. 9 squared is 81. 27 plus 4 is not 81. 100 equals 34. No, it does not. False, false. 64 equals negative 24 plus 4, which is negative 20. So 64 does not equal negative 20. So that's false. So we could sit here and just try different values all through this. And so then over here they have the values written down. And 5 is not a solution, 6 is not a solution, negative 7 is not, 0. And they put all the values that are not solutions over here. But the one that is a solution is up here. So they're sifting through values and they're finding solutions, and they get through the filter where the others do not. That's what this diagram is showing. Okay, page 2 brings us to example 2, and it says to consider the equation 7 plus p equals 12. Okay, so let me highlight that. Here's our equation. Alright, so with that, we're going to just choose random values. So if I substitute in 0, 7 plus p, p equals 0, 7 plus 0 equals 12. No, 7 does not equal 12. So they wrote false over here. Let p equal 4. 7 plus 4 equals 12. 11 equals 12. That is false. Okay, let me change colors here. Let p equal 1 plus the square root of 2. So it would be 7 plus, and then 1 plus root 2 equals 12. Well, that would be 8 plus root 2 equals 12. Well, the square root of 2 does not equal 4, so I know that's false. Square root of 2 is 1 point something. Let p equal 1 over pi. So now they're saying 7 plus 1 over pi equals 12. Well, that's obviously not true because that's irrational, so that's going to be false. And then finally let p equal 5. So 7 plus 5 equals 12. That there is a solution, so that is true. Okay, so the solution set of an equation written with only one variable is the set of all values one can assign to that variable to make the equation a true statement. Any one of those values is said to be a solution to the equation. To solve an equation means to find the solution set. That means all solutions for that equation. Okay, so if I were to do a Venn diagram of this, either there's a solution or there isn't, so it's disjoint, and this is the false side and this is the true side. So if I did this, well, what was false? 4 was not true. 1 plus the square root of 2 was not in the solution set. 1 over pi was not in the solution set. 0 was not in the solution set, but over here in the solution set was 5. But 5 may not be our only solution depending on the type of function we had. In this case, 5 would have been the only solution, but there are others who would have more. Okay, so example 3 now says to solve for a squared equals 25. So if we take a squared, set it equal to 25, well, in order to get a variable by itself, you have to move everything over to the other side of the equal sign, which means to do inverse operations to cross an equal sign. So this inverse operation of squaring is square root. So I take the square root of a squared to get rid of that squared. And what you do to one side, you have to do to the other, or it is no longer true. So I take the square root of both sides. The square root of a squared is a. And the square root of 25 is plus or minus 5. So in this case, there were two solutions. So if I had a solution set Venn diagram where this was true and this was false, then I'd have 5 in here and I'd have negative 5 in here, and it doesn't matter what else I put in there, it is not going to be a solution. So the rest of the number set, all real numbers other than 5 and negative 5, would be in the false set. The true would only have 5 and negative 5. Okay, page 3 brings us to a little bit of information we need to go through, and it says one can describe a solution set in any of the following ways. In words, you could say a squared equals 25 has solutions 5 and negative 5. A squared equals 25 is true when a equals 5 or a equals negative 5. In set notation, the solution set of a squared equals 25 is bracket negative 5 comma close bracket. In a graphical representation on the number line, the solution set of a squared equals 25 would be the number line with a dot solution at negative 5 and 1 at positive 5. In the graphical representation, a solid dot is used to indicate a point on the number line that is to be included in the solution set. Warning, warning, the dot one physically draws is larger than the point it represents. One hopes that it is clear from the context of the diagram which point each dot refers to. So in other words, this is not a set of numbers including 5.01, 5.02, 5.03 is what they're trying to explain when they have a dot that's fairly large. Okay, so now it says how set notation works. The curly brackets indicate we are denoting a set. A set is essentially a collection of things. Example, letters, numbers, cars, people. In this case, things are numbers. From this example, the numbers negative 5 and 5 are called elements of the set. No other elements belong in this particular set because no other numbers make the equation a squared equals 25 true. When elements are listed, they are listed in increasing order, so you would not put bracket 5 comma negative 5. They're always increasing from left to right, just like on the number line. So they'd be in order of a number line, in other words. Sometimes a set is empty. It has no element, in which case the set looks like brackets with nothing in it. Okay, that means the empty set, and we often denote this with a symbol that looks like a 0 with a line through it. Okay, so we refer to this as the empty set or the null set. Okay, so exercise 1, it says to solve for a squared equals negative 25. Present the solution set in words, in set notation, and graphically. Okay, so try this, pause the video, and then come back and we'll check it. Okay, so assuming you've done this, in words, I would say a squared equals negative 25 has no solutions. A squared value can never equal a negative. There is nothing I can substitute in for a and get a negative number. In set notation, it would be this bracket or the empty set. In graphical representation, it would just simply be this number line, 0, 1, 2, 3, -1, -2, -3, and no solutions written down on it. There are no dots on that number line. It would just be an empty number line. Okay, page 4 brings us to exercise 2. Try this, pause the video, and then come back and check your answer. Okay, depict the solution set 7 plus p equals 12 in words, in set notation, and graphically. So if I took 7 plus p equals 12 and subtracted 7 from both sides to isolate that variable, I get p equals 5. So I would say, in words, 7 plus p equals 12 has the solution p equals 5. Set notation, bracket, the number 5, bracket. Graphically, a number line, 0, 1, 2, 3, 4, 5, -1, you get the idea, -2, -3, good enough. I'm going to put a dot right here on 5. Okay, so there's, in words, set notation, graphically. Example 4. Solve x over x equals 1 for x over the set of all positive real numbers. Depict the solution set in words, in set notation, and graphically. So anything divided by itself is 1, and hear what I just said, anything except there is one value that we can't use, so we'll get to that in a moment. So anyway, they gave us this table. Let x equal 2. 2 over 2 equals 1, true. X equals 7. 7 over 7 equals 1, true. Let x equal 1/100th. 1/100th divided by 1/100th equals 1, true. Let x equal 562 2/3. Well, that's also equal to 1 when you divide it by itself, true. And 10 to the 100 divided by 10 to the 100 is 1. That is also true. Let x equal pi. There's an irrational number. Irrational number divided by that same irrational number is still equal to 1. That is also true. Okay, so depict the solution set in words, in set notation, and graphically. Okay, so here we go. One needs to be very careful. The set of all positive real numbers. Okay, so they are restricting our domain. So we aren't talking about negatives. So in words, a solution set is all positive real numbers. Okay, in set notation. Okay, now this is how we would do this. We would say the set of all x that are real. And then there's this long line here, and we say the word such that when we put that there. So let me just not make that so messy. Such that, so set notation, bracket, x, real. The set of all x, that's how you say this, the set of all x that are real, such that x is greater than 0, close bracket. Okay, so that means all x is greater than 0. If they're real, then they're in this solution set. And let's read this again. This is read, the set of all x that are real, such that x is greater than 0. Graphically represented, we would have a number line. Here's 0, here's 1, here's 2, and so on, -1, -2. And it's not equal to 0, so whenever we're not including that value, we put an open circle. and then we're going this way, and we are shading the numbers line. All decimals, fractions, rational, irrational, as long as they're positive, real, they're solutions. Okay, page 5 brings us to exercise 3. Pause the video, see if you can do this. And here we go. Exercise 3 says, solve x divided by x equals 1 for x over the set of all non-zero real numbers. Okay, so there's our restriction on our domain. All reals, not including 0. Describe the solution set in words, in set notation, and graphically. Okay, so in this case, they eliminated the only solution that is not true. Okay, so in words, we would say this right here. We would say in words, the solution set is the solution set is the set of all non-zero numbers. The set of all non-zero real numbers. Okay. And then it says set notation. We'd say the set of all x that are real such that x does not equal 0. That's the easiest way to do that. List what you can't have, everything else is true. Graphically represented would look like so. We have this number line, here's 0, we don't include it, here's 1, here's 2, here's 3, -1, -2, -3. This is going to be true going this way forever. Everything in between, and this is going to be true going this way forever. So really it's the entire number line except 0. Okay, example 5. Solution for x colon x times the quantity 3 plus x equals 3x plus x squared. Okay, so we want to solve for this. So the first thing we want to do, there is an x outside here, which means this is this times this, and this has x's over here. So there's a couple different ways we could do this. I could distribute and get 3x plus x squared, okay? Or I could divide by x, like so, and what you do to one side, you do the other. Only do this if you can cancel, you have like terms. No, I'm sorry, erase that, they are not like terms. If you have the same variable in both terms of the expression, then you can get rid of it. Common factor, or it's a factor of both. So these x's cancel, and I get 3 plus x equals. This x will cancel with that, leaving me with 3, and x squared divided by x is x, so it's 3 plus. These x's cancel, leaving me with 3 plus x equals 3 plus x. That's a little messy there. 3 plus x. Now if I want to get all my x's on one side, I subtract x from both sides, and I get 3 equals 3. Now whenever you get a situation like this, and you end up canceling all the variables, and you get a number equal to itself, that is the set of all reals. That means every single thing would work. If these were different, then it's not true ever, and there'd be no solution. But in this case, I would say the solution set in words would be the set of all real numbers. So you'd say the solution set is the set of all real numbers. Okay? Graphically, it would be the set of x that are real such that, and then you'd be like, wait a second, what do I put over here? The set of x that are real such that x is real. that doesn't really make sense, so how about we just do this? There is a symbol for the set of all reals, and it looks like an R with an extra line through it. So that would be our answer right there, the set of all reals. So you'd say the solution set is the set of all reals. Graphically, well, that would just simply be a number line, 0, 1, 2, 3, -1, -2, -3. And then I would take, and let's just make this simpler, and I will choose this, and I will choose thicker, that's fine, and I will choose red to show my solution, and I'll put a, and I do that, and then I do it again this way. So that is what it would look like. All reals is the set, and there wouldn't be a dot here, I just chose that ray and it shows a dot, so it's just arrows, double arrows, everything included. Okay, exercise 4. Solve for a plus a squared equals a times a plus 1. Describe carefully the reasoning that justifies your solution. Describe the solution set in words, in set notation, and graphically. Okay, so in this one, I'm not going to do what I did here. I'm going to distribute. So by the distributive property, I'm going to say, whoops, forgot to switch back to my pen. I'm going to say a plus a squared equals a squared plus a, because I distributed, okay? So by the distributive property, we have a plus a squared equals a squared plus a. This is a true numerical statement no matter what value the sign of a, or what we assign to a. So what I'm saying is if I subtracted a squared over here and subtracted a squared over here, I would get a equals a, because these cancel and these cancel. Well, if I subtract a and subtract a, I get 0 equals 0. So whenever that happens, then we are going to have a number statement no matter what real value we assign to it is going to be true. So the solution set is a set of all reals. So that's what we would say. The solution set is the set of all reals. Okay? In set notation, that would just be the symbol for the set of reals. And graphically, it would again be this right here. I'm not going to redraw it, but it would go down here. So down here it says an identity is an equation that is always true. So whenever we have something equal to itself and we get this, or we get like example 5 here, that is an identity equation. No matter what we substitute in, it will always be true. Okay, here's page 6. More exercises. So pause the video, see if you can do these on your own, and then come back. Okay, here we go. Identify the properties of arithmetic. Identify the properties of arithmetic that justify why each of the following equations has a solution set of all real numbers. So looking at A, it says 2x squared plus 4x equals 2 times the quantity x squared plus 2x. Well, if I distribute, I get 2x squared. And if I distribute, I get plus 4x, and that's equal to the left. So this is the distributive property. Okay, part B. 2x squared plus 4x equals 4x plus 2x squared. So A plus B equals B plus A. That means order doesn't matter. That is commutative property of addition. Okay, make sure you say that because there's addition and there's multiplication. Here we're adding. Part C. C says 2x squared plus 4x equals 2x plus 2 plus x. Okay, this could be the distributive property. We're distributing and getting 4x plus 2x squared. So that's the distributive property. It's also the commutative property, where order doesn't matter. commutative property of addition, and it could also be associative property of multiplication if we analyze the interpretation of 2x squared with extreme care. All right, but anyhow, this is definitely distributive property as well. Okay. Okay, exercise 6 says to create an expression for the right side of each equation such that the solution set for the equation will be all real numbers. There's more than one possibility for each expression. Feel free to write several answers for each one. Okay, so there's many things I could do. I could just simply multiply this by 5 and say, well, 5 times 2x is 10x minus 5 times 5 is 25. So there's a multiple of 5. That's easy enough. There's many we can do, but I'll just stop there. Here I'll factor. I see that they both have an x value, so that'd be x plus 1 times x. And 4 times x times y times z. Well, let's see, what could we do? Just put them in different orders maybe. X times 4 times y times z. So that's the commutative property of multiplication. And this I could just FOIL and say x squared plus 4x plus 4. Okay, but there's many other solutions. Okay, this is page 7, example 6. Solve for w, where w plus 2 is greater than 4. So in order to solve this, I want to get w by itself. So I do the inverse of addition. So I subtract. Actually, I don't want. Let's try that again. So it's going to be minus 2 on both sides. So when I do that, I get w is greater than 2. Okay? So in words, w must be greater than 2. So w must be greater than 2. In set notation, you would say the set of all w that are real such that w is greater than 2. Okay? And graphically, you would have this number line here. Actually, let's make this a little neater. I'll bring in a number line. Okay, so here's a nice, neat number line. And what I'm going to do is the solution is w is greater than 2. So I'm going to draw a line going here, like so. The arrow's only going one way, and I want to also put a dot here that is open. Okay, so that is the set of all w such that w is greater than 2. Exercise 7 says to solve for b, where b squared is greater than or equal to 9. Describe the solution set using a number line. Okay, so this is so the first thing I would do is take the square root of b squared. Has to be greater than or equal to the plus or minus square root of 9. That would give me b has to be greater than or equal to plus or minus 3. Okay, so in this situation we have to be careful. If I choose 0, is it true or false? So that's what I would do. So if I'm going to use this same number line, let me bring in the number line. Okay, so here's my number line. So if I'm going to graph this, first thing I want to do is, well, how can b be greater than and less than, or greater than or equal to positive 3 and negative 3? So I'm going to choose some values to see what's true. So plug in 4. 4 squared is 16. 16 is greater than 9. That is true. Okay, so the greater than or equal to tells me that I have a point at 3. 3 squared is 9. 9 equals 9. So that's a true statement. So it's going to be this direction here. Okay, so that just verifies values greater than 3. But what about values greater than -3? Well, then that would put a dot here. Don't do this yet, just watch. And go this way, and then we're overlapping our original answer and going back 6 units from 3 to -3. All right, but that may not be the solution. Choose 0. 0 squared, is that greater than or equal to 9? 0 greater than or equal to 9? No, that's false. So these values are all false. So b greater than or equal to plus or minus 3. Think of the -3 rather than writing it this way. Let's just use the positive here. And I would say that would mean b is greater than or equal to 3. But then if I want the negative side, I am multiplying by -1 to get a -3. And what does that do to my inequality? Well, it flips it. So it would be b is less than or equal to -3. So less than or equal to would be here, and that would be going this way, shaded. And then I can check. Well, -3 squared is +9, and that equals 9. -4 squared is +16. That's greater than 9, so that's true as well. So here is our number line solution. Okay. The answers are 3 and -3, and then we need to decide which direction these are going. So there is a trick to that. If it is greater than, it's going opposite directions, and if it has a less than symbol, it's in between. Okay. Part B says, what is the solution set to the statement? Sticks of lengths 2 yards, 2 yards, and L yards make an isosceles triangle. Describe the solution set in words and on a number line. Okay, so think of a triangle, and it says isosceles. Okay, well, if we just have a triangle, equilateral triangles are where the sides are all equal. Scalene is where they're all different. Isosceles is when we have two sides that are congruent. Okay, so we have to think about restrictions of our domain. Well, I can't have a side length of 0, or I wouldn't have a triangle. I'd have an angle if this was gone. If this side length were 0, then it wouldn't be a triangle. We wouldn't have a third side. So it's got to be greater than 0. Okay, so if I do a number line again, so let me just copy this down, bring a number line down. Okay, and I'm just going to fill this in pieces. I know that it's got to be greater than 0, which means that I don't have a dot that's shaded in on 0. It's just an open circle. I know that it's got to be greater than 0, and I know I can't have negative length, so I'm not even worried about over here. So now I'm just concerned with values to the right of 0. All right. So sticks of length 2 yards. 2 yards and L. So that means this is 2 yards, this is 2 yards, and this is some unknown value L. Well, if L is longer than the sum of these two sides, then they would not reach the endpoints. So if I had a stick of length 2, and then another stick of length 2, and the third side was longer, well, there's no way I can make this a triangle, because if I move this, oh, they're all one piece, now they're not. If I move this over here, let's move it back because I can't grab it now. Let's rotate it first. If I move this over here and put it there, and if I rotate this and move it over here, okay, see how they don't reach? I can't make a triangle. So I know that the L side can't equal 4, or the lines would these two would just lay on top of it. It still wouldn't be a triangle. So now I know the sides have to be less than, L has to be less than 4. So my solution is all values between 0 and 4. Okay, page 8 brings us to the end of lesson 11. Review the lesson summary and go do your problem set.